Section 3.9, Derivatives of Logarithmic and Exponential Functions. So we've already talked about in previous sections the derivative of e to the x. And the derivative of e to the x is e to the x. A newer derivative is this derivative of the natural log of x. So we're saying that the derivative of the natural log of x is 1 over x. Now if we have a different base than base e, it's a slightly more complicated formula, but not too bad. So let me derive the derivative of a to the x for you. Okay, so we can rewrite a to the x as e to the natural log of a to the x. And we're allowed to do that because of the nice composition of inverse functions properties that exists. Okay, so since e to the x and the natural log of x are inverse functions, the composition of the two of them is just going to equal x. So in this case our x is a to the x. Okay, so we have e to the ln of a to the x is equivalent to a to the x. So if we take the derivative of this quantity using an already known property, okay, we already know that the derivative of e to the x is e to the x. So the derivative of e to the ln of a to the x is e to the ln of a to the x times the derivative of that exponent. So maybe I want to back up a step here, because finding the derivative of the exponent is actually not too bad, but we need to apply a logarithm property. So let me add a middle step here. I'm going to rewrite e to the ln of a to the x as e to the x times the natural log of a. And that's really the whole point in using this composition and of exponentials and logarithms, is so that we can utilize the nice properties of logarithms that allow us to rewrite an exponent in the argument as a multiplier down front. Okay, so now if we take this derivative, we have e to the x times ln of a, and then using the chain rule, we multiply by the derivative of the exponent. Now ln of a is just a constant, so x times a constant, the derivative of that, is just the constant ln of a. And I already said that e to the x ln of a is equivalent to a to the x, so this whole quantity is equal to a to the x times the natural log of a. So that's our nice little formula for the derivative of a to the x. It's equal to a to the x times the natural log of a. So the difference between a to the x for a general base a and e to the x is that for a to the x we have an extra term. We have that natural log of a. But keep in mind that the natural log of e, you could really add that on right here, because the natural log of e is just 1. Okay? Alright, so the derivative of log base a of x. So now we have a general base a, not necessarily base e, and we want to find the derivative of that. So the idea here is that we're gonna use kind of a placeholder variable. That's what I like to call it. So I'm gonna let y equal log base a of x. Okay, and so what I'm really trying to find here is the dy dx, essentially. All right. But the nice thing about writing it out as an equation here, y equal to log base a of x, is that we can transform this to an exponential equation, and then we can use implicit differentiation to find dy dx. Okay, so let's transform it to an exponential equation. So we are transforming to an exponential. And if we do that, we get a to the y equal to x. Okay. Now I'm going to use implicit differentiation. So I use implicit differentiation. I'll just just abbreviate that. And we're going to find dy dx. So if we take the derivative of a to the y, we just found a formula for that. It's a to the y times the natural log of a dy dx is equal to the derivative with respect to x of x is 1, and therefore dy dx, oops, it's not writing for some reason, dy dx is equal to 1 over a to the y times the natural log of a. However, a to the y is equal to x from up here. So we have that dy dx is equal to 1 over x times the natural log of a. Okay, and so that's how we get that the derivative with respect to x of log base a of x is equal to 1 over x times the natural log of a. So if we compare that with the derivative of natural log of x, the difference is we're dividing by an extra term, the natural log of a. Alright, let's see an example. Alright, so suppose we want to find the derivative of 2x plus 1 to the pi power. So pi is just a number. We treat it just like any other exponent. So f prime of x is equal to pi times 2 to the x plus 1, all raised to the pi minus 1 power. And then applying the chain rule, we multiply by the derivative of 2 to the x plus 1, which is 2 to the x times the natural log of 2. And we can clean it up a little bit. We can put the constants out front. Pi times the natural log of 2 times 2 to the x times this 2 to the x plus 1, the quantity to the pi minus 1 power. And we're done. Okay? Next example. Alright, what if we want to find the derivative of the natural log of the quantity x plus 1 over x minus 1? So we have a rule that the derivative of the natural log of x is equal to 1 over x. So we're going to apply that, but we're also, since we have an argument that's a little more complicated than just x, we have to use the chain rule. So let's see what this would be. So the derivative of the natural log of x plus 1 over x minus 1 is 1 over the argument x plus 1 over x minus 1 times the derivative of that argument, which we'll have to apply the quotient rule. So we have denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all over the denominator squared. And I can rewrite this first fraction as its reciprocal, x minus 1 over x plus 1. And we're multiplying that by, let's see, x minus 1 minus x minus 1, all over x minus 1, the quantity squared. So the x's, x minus x adds to 0. So now we've got x minus 1 over x plus 1 times minus 2 over x minus 1, the quantity squared. And that simplifies down nicely to minus 2 over x plus 1 times x minus 1. Okay, so that's how we would handle a derivative like that. Lastly, I want to give you an example of yet another technique. Okay, so most of this section is learning the rules for taking the derivatives of logarithms of different bases and exponentials of different bases, but there's also a few examples of something called logarithmic differentiation. And logarithmic differentiation is a really nice technique that will really help you with certain types of derivatives. So for example, the example I'm going to show you is sine of x all raised to the natural log of x. Okay, so something like that, we have a function of x raised to a function of x. It's very tricky. There's no formula for it. Okay, it's totally different from the derivative of a to the x, where a is a constant. Okay, now we have a function raised to a function of x, so it's different. So logarithmic differentiation is probably what you want to use in a scenario like this. So anytime you see a function, so for example, just a regular function h of x raised to another function as its power, you might want to think about this logarithmic differentiation idea. Okay, so let's see how this is handled. So f of x equals sine x to the natural log of x. What if I take the log of both sides? Let's see what happens. And I'm actually going to rewrite f of x as a y. And now I'm going to take the log of both sides. So the reason behind doing this is because logarithms have a lot of really nice properties that allow them to be rewritten in helpful ways. So now what I can do is I can rewrite the right-hand side as the natural log of x times the natural log of sine of x. And this is now something that we know how to take the derivative of. This is going to involve the product rule, which we've already learned. So ultimately I want to find dy dx. So notice I have natural log of y on the left hand side, so instead of solving for y, I'm going to use implicit differentiation. So you can start to see how things really build. Okay, all the techniques that we've been learning in chapter 3, they're all combining to allow us to solve more complicated derivatives. Alright, so using implicit differentiation, I will have 1 over y prime, is equal to, now we've got this product, so remember we are taking the derivative with respect to x, so we have the first times the derivative of the second, which is 1 over sine of x times the cosine of x, plus the second times the derivative of the first, which is 1 over x. So we can write that as 1 over y prime equal to the cotangent of x times the natural log of x plus 1 over x times the natural log of sine of x. And solving for y prime, we multiply both sides by y to get y times the quantity of the cotan x ln of x plus ln of sine of x over x. But y is equal to sine of x to the ln of x, so we can simply put that in here, and we're pretty much done. Okay. So here's our final result. That is our y prime. So it looks complicated, but honestly without logarithmic differentiation it would have been much more difficult. Another area or another type of problem you might want to think about logarithmic differentiation for would be problems that involve things like 3y plus 5, I guess I should keep this as x. Maybe something like 3x squared minus 7y to the 6th power times the square root of 2 minus 7x over the quantity x squared plus x minus 7 to the 5th. Something that would just be monstrous if you were trying to use the product rule and the quotient rule. If you use logarithmic differentiation on something like this, you're going to be able to separate a lot of the terms and make your differentiation process a lot easier. Okay, so be on the lookout for problems that look like this, just absolute bears for trying to use the quotient rule and the product rule combined, and problems where we have a function raised to a function. Okay, those are both indicators that you want to think about using logarithmic differentiation.